Hi, everyone. My name is Jerry Harp. I'm a physicist at the SETI Institute working in the SETI group. And it's my pleasure today to introduce Michael Peskin from the SLAC National Accelerator Laboratory at Stanford, where he has been since 1982. So he's one of the few people who have a job that lasts for a long time. He took his PhD at Cornell with Ken Wilson in 1990. Oh, no, yeah. Never mind that. Sometime earlier. And very interesting, he's the author of Introduction to Quantum Field Theory. So this is the textbook that is used in graduate school in many, many physics departments. And so he was telling me about how he often runs into people who used his book for their coursework, and that book came out in 1995. So without further ado, today Michael Peskin is going to talk about the Large Hadron Collider, stage 2.
Okay. Well, thank you very much. Well, it's a pleasure to be here. This is my second time giving the SETI colloquium. The first time was 4 years ago in, I believe, April 2012. I gave at that time an introduction to the program that was really just starting up at that time of the experiments at the Large Hadron Collider at the laboratory CERN in Geneva, Switzerland. I gave my opinion in that talk that something called the Higgs boson would be discovered. And someone in the audience waved a check at me and bet that I was wrong. And my reply was, I'm a professional, I shouldn't take your money. So in any event, as you probably know, this CERN Large Hadron Collider is the world's largest facility for particle physics. I'll talk a little in more detail about how it's set up and how the experiments are done as the talk proceeds. Right now, the LHC is beginning its second round of operation, run 2, at an energy much higher than the energies that were at which it operated in the earlier years. And so I think now, in the first run, there was this particle, which we'll talk about, for which the purpose of the experiments was to find that. Now, the purpose is to somehow go beyond and find whatever is there. And I must say that even theoretical physicists like me don't have a clear idea of what particular particles are expected to show up, except that something should show up there. And so what I'd like to do in this talk is to give you a little introduction to what these experiments are looking for, what the aim is, what has been achieved so far in these experiments in terms of characterizing the heaviest and most mysterious elementary particles, and then try and explain to you how we go beyond that to try and find new kinds of elementary particles and maybe new forces of nature. So I think, first of all, let's just get oriented. Usually when you come to the SETI colloquium, you're going out into space to planets, the galaxy, clusters of galaxies, maybe the entire universe. I hope you've had some talks about the shape of the entire universe. But, do you have a pointer or? No, I have one here. Excuse me. But in this talk, we're going to go in the opposite direction. We're going to go to the very small, because I think you also have the idea that as things get larger, you come to the grandest structures in the universe. But as you go smaller, you come to the most fundamental structures. So if you want to know ultimately what are the equations of motion of nature, the equations that in Einstein's conception God wrote down and everything follows from that, what you have to do is to find the most basic elements of nature and the most basic forces. So here's about where we are now. So this is the atom. Atoms are very large things in my conception, enormous. You might think of them as the Earth. The size of an atom is a tenth of a nanometer. So if you think about nanoscale physics, that has to do with arrays of atoms, individual atoms, which people manipulate. And that's a very fascinating science, but it's not the subject of this lecture. One other thing that you could do is to think about the atomic nucleus, which is 100,000 times smaller than that. So if you compare it to the Earth, the atomic nucleus is about the size of a basketball court. And there we know, actually, that the atomic nucleus is composed of protons and neutrons, which are themselves composed of more elementary particles called quarks. Here I've shown the up and down quarks that make up the protons and neutrons inside the helium-4 nucleus. But please excuse me, for the things that I think about, the nucleus is also a very large object. And so what we want to do is to go down from that to the very limits of human knowledge. So we go down by another factor of 1,000 to structures which, according to this basketball analogy, are the size of a basketball. And there we find the particles that carry the elementary forces of nature. It used to be the main question for the physics of elementary particles: what are the forces that act at the size of a nucleus, and how do those forces work? Over the past few decades, we've actually solved that problem and come to a very beautiful and coherent theory which goes by the boring name of the Standard Model of particle physics. And what we're trying to do now is to rip that paradigm open and to find, even at a lower level, what can be there to basically resolve the questions that this, quote, standard model cannot answer. So what we're trying to do, here's where we are now, understanding things that are, as you see, 100 million times smaller than an atom. And what we're trying to do at the Large Hadron Collider is to go to things even smaller than this and to try and understand the as yet unknown forces that are operating there. The program started, I guess, with this experiment, of which I'll give you a little diagram. This is 1909. It's called the Geiger-Marsden experiment because the leader of this group, Ernest Rutherford, didn't touch things in the laboratory. Geiger is the inventor of the Geiger counter, of course. And they took a radium source. They shot whatever comes out of radium in its radioactive decay at a gold foil. They were looking at things that would, these are alpha particles, would go through the gold and be perturbed by their interaction with atoms and then come out the other side. But Rutherford suggested that they turn the experiment around and put the detector on the same side to see if anything would scatter back. And indeed, what they found was that some alpha particles very rarely would scatter back from the gold foil. And Rutherford described this as if you had shot a cannon at a piece of tissue paper and had something recoil from you. And this was the discovery of the atomic nucleus. And then since then, there have been many generations of experiments. This is more than 100 years ago now. Many generations of experiments that have refined our knowledge of the atomic nucleus. And three of the very important figures in that discussion, here's Mr. Rutherford. This fellow, James Chadwick, discovered the neutron. So he discovered the structure I showed you a moment ago, that the nucleus is made of protons and neutrons. Enrico Fermi famously formulated the theory of radioactive decay and argued that actually there were two different forces that acted at the nuclear level, one called the strong interaction, which binds the protons and neutrons together, and the other called the weak interaction, which was the mechanism of radioactive decay. So many years later, we come to this group of three figures, who are the people who formulated what I now call the standard model. So these are Sheldon Glashow, Abdus Salam, I'm sorry for the resolution of this picture, and Steven Weinberg. They look very smug in this picture because they're about to receive the Nobel Prize. And unfortunately, Mr. Salam is no longer with us. But actually, Steven Weinberg I visited in Texas last fall, and he's still looking very smug because at the moment, no one has been able to overturn this theory with a more fundamental point of view. Here is some artist's rendition of the structure of this theory. It contains matter, it contains forces, but in quantum mechanics, all forces are actually particles. Any force, according to relativity, is transmitted by a wave equation, and any wave equation can be quantized if you believe in quantum mechanics, for which I think you should. There's a lot of good evidence for it. And when you quantize a wave equation, you find basic quanta, which are particles. So at this level, where quantum mechanics and the theory of relativity are playing an essential role, there's, in some sense, no difference between interactions and particles. And every kind of interaction has a particle that carries it, and vice versa. So the way nature is made up, the things around the outside are matter. Up here, the quarks, which are the constituents, as I've told you, of the nucleus. And then there are various kinds of heavier quarks, which are somehow associated with the familiar quarks U and D that appeared on the previous slide and decay into them. We have no idea why there are 6 quarks. 2 seem to be perfectly sufficient to make up all the matter that we see in this room. And on the other hand, the leptons. The electron is very familiar. It's the basis of all modern technology. These other leptons are extra in some way. The electron neutrino is a particle which is almost massless, not quite, has 0 charge. Its mean free path in matter is light years. It's a very mysterious particle. It turns out that there are 3 of them. Again, we have no idea why there are so many, why there's anything more than the electron, which is just the thing we need to complete the structure of atoms. The next ring, the blue ring, are the carriers of forces in the standard model. Electromagnetism is due to the photon. The strong interaction is due to a particle called, somewhat unimaginatively, the gluon, because it glues things together. The interactions of radioactive decay are carried by the W boson and the Z boson. And once again, all of these force-carrying particles are associated with wave equations. And actually, all of those wave equations have the form of the famous Maxwell equations of electromagnetism. So in some sense, the standard model is no surprise. It just says that not only does electricity and magnetism obey Maxwell's equations, but all of the forces of nature, strong, weak, and electromagnetic, obey a kind of generalized Maxwell equations, each in its own domain. And in the center of this diagram, you see the Higgs boson, which is the thing that forms a field that fills all of space and is responsible for the masses of all of the other particles. Actually, in this talk, I decided not to make the Higgs boson the main focus. I'll tell you just a few things about that. Afterward, if you have other questions about that, I'm happy to answer them. Okay. Maybe I should say that this theory, in its own domain, is extremely accurate. This is what is called the line shape of the Z boson. So you can do the following experiment, and we did this experiment at SLAC, and also people at CERN did this experiment in the 1990s. Take a beam of electrons and take a beam of positrons and shoot them at one another and try to cause them to annihilate, the matter with the antimatter. Now, if you adjust the energy so that the energy is exactly the energy mc squared that you need to make one Z boson, the rate of annihilation increases dramatically. It increases over the background level by about a factor of 1,000. And at that energy, you have an enormous increase in rate. And what you're doing is that you're making individual Z bosons at rest in the laboratory. And so in these experiments, people were able to study these Z bosons and measure their properties. In particular, because the Z boson is unstable, because of the Heisenberg uncertainty principle between energy and time, the energy of the Z is slightly undefined. Again, it's a Heisenberg uncertainty principle. And what you can do is then say, well, it's not exactly at the energy mc squared, but at a range of energies around that. And if you're very clever with your quantum theory, you can actually predict the shape of the rise and fall of the enhancement in the rate due to the Z boson. So that is the black line that you see here. The theory of that line is very sophisticated because it's not only the simple coupling of electrons and positrons. The electrons and positrons can radiate photons on the way in. The Z radiates gluons when it turns into quarks. Actually, all three of the interactions of the standard model appear in the theory represented by the black line. But it's a one-parameter theory. It just depends on the position of the resonance, and from that you can compute everything else. The little red things are the measurements of this curve done by the Opal experiment at the big collider LEP that ran at CERN in the 1990s. And yes, there are error bars on those points, as people in the front row can attest. And this is it's a parts per mil verification of this particular aspect of the theory. And it's one of the things that tells us that we really understand this theory of weak interactions of Glashow, Salam, and Weinberg extremely well. On the other hand, there are a lot of things that this standard model doesn't explain. And probably the three most prominent I've written on this slide. First of all, the astrophysical dark matter. So it's funny that when you go to particle physics, you immediately talk about astrophysics. But of course, something that's in the universe should reflect itself in the basic laws of the universe. I hope you've heard in other colloquia, again, I didn't make this a main topic of this one, that 80% of the matter in the universe is in the form of a kind of matter called dark matter. It has zero electric charge. It's very weakly interacting. It's probably heavy. The thing we know about it is that in the universe today, it's moving non-relativistically. So if it comes from the Big Bang, it's probably a very heavy particle. And there's no place for this in the standard model. We have no idea what it is. This picture shows one of the very important demonstrations of the existence of dark matter in a galaxy, a set of two clusters of galaxies called the Bullet Cluster. So this diagram shows that dark matter is distinct from ordinary matter. Roughly, the blue here is the dark matter, and the red is the gas, which is the main component of a cluster of galaxies. But there's no place for this in the standard model. We need to find some completely new type of particle that could make up this dark matter. The second, well, here are some rocks, is the fact that the universe contains matter and no antimatter. The initial condition of the universe, we actually don't know what that is, but the most persuasive cosmological theory today, the theory of inflation, which explains all of the structure in the universe, the perturbations in the microwave background. The prediction of inflation is that the initial conditions of the universe were absolutely symmetric between matter and antimatter. No net matter, no net antimatter. And yet here we are, we're made of matter. There are no antiprotons in sight. If there were, I don't know, even 1 part per billion antiprotons in this room, you'd be radioactive and you couldn't live. And so why did that happen, to go from a state with no net excess of matter or antimatter to the state that we live in today when it's all matter and no antimatter? The standard model doesn't explain that. For that, we may not need a new particle, although theories of this generally contain new particles. But we certainly need new interactions in nature that are not in this extremely well-tested theory that I just described to you. And finally, there's the question of the Higgs field structure. So you remember I told you that this Higgs field, the thing that was at the center of the diagram, is a constant field that fills space. And when particles move over it, the up quark, the top quark, which we'll talk about later, the W boson, they get mass. In order for that to happen, there has to be a reason why this field is not just a fluctuating field like all the others we see in nature, but somehow it forms structure in empty space. And that's a mystery that we don't understand, and one, again, that is not explained by the standard model. So for all of these reasons, we believe that there are new interactions in nature, and that if we somehow went down deep enough, we would find them. And as I told you already, new interactions mean new particles. So we'd like to go looking for new elementary particles. That's now the quest of the LHC, and so let me describe to you how that quest is being carried out. Now, in the rest of this talk, I'm going to show you a lot of event displays. So an event display is basically a picture of an elementary particle reaction. However, the camera is somewhat exotic. Elementary particle reactions occur very rapidly. Particles move at the speed of light. These particles have very unusual properties with respect to the photons that are caught by a camera. And so you need a very special kind of camera to be able to take these pictures. The LHC cameras are very large and complex. And I'm going to show you a lot of event displays. So let's just practice a little on some of these event displays that were gathered in the Z0 experiments that were done at SLAC in the 90s. The camera there is this detector called the SLD detector. This is a human, so you get an idea that this is already a 4-story high device that sat in some back lot at my laboratory. The structure is the following. The beams, the electron and positron beams, come in along an axis. And then you wrap that axis with various detection devices, which are cylinders, one inside another, each kind of detection device doing a different job. For the SLD, the inner detector, which is this green thing, was a chamber filled with gas. Particles, charged particles going through that gas would make ionization, and then you would read that ionization out locally, and it would give you the path of the particle. If you put that object in a magnetic field, the particles bend this way for a positively charged, this way for a negatively charged particle, and you can find the momentum of the particle. So that's what I would call the tracking chamber. Nowadays, in the LHC, this is all done with silicon. You put silicon wafers in the path of a particle, and a particle that impinges one of those wafers leaves an electronic signal that you can read out. The next thing that you see in red is called an electromagnetic calorimeter. In this case, it's made of liquid argon, so they're pieces of lead in a bath of liquid argon. These are heavy materials from the bottom of the periodic table. And what they do is to take things with electromagnetic interactions, in particular photons and electrons, and convert them to a stream of electron-positron pairs. The ionization from those can then be read out, and what it measures is the total energy deposited by photons, gamma rays in this case, and electrons. Around that in yellow, what's called the hadron calorimeter. So these are plates of iron with various detection devices between them. And those are supposed to range out pions, the strongly interacting particles, protons, pions, neutrons, sigma baryons, whatever you have, to measure the total energy of nuclear particles that come out of the reaction. And finally, anything that can get through the whole thing is probably the particle called the muon, the particle which is the primary constituent of cosmic rays. And a muon is like a heavy electron. It has the same interactions as the electron. It's 200 times heavier. Again, nobody understands why these particles exist, but we measure them. That's where they are. If we can understand why they'd exist, that would be a big advance in particle physics. So let me now show you a couple pictures taken with this camera. Here's the simplest one. This is the Z0. Remember, in these experiments, we're creating Z particles at rest and watching them decay individually. Here's a Z decay to 2 electrons. You see the tracks in the tracking chamber. This tower is a histogram which shows you the energy deposition in the electromagnetic calorimeter. So these are electromagnetic objects. This picture shows another kind of lepton. Remember I told you about the electron and the muon. There's a third kind called the tau lepton, which is 20 times heavier than the muon. Again, nobody knows why this particle is there, but it is definitely there. This is the signature of the tau lepton. You see tracks, you see electromagnetic deposition. This is basically an electron from a tau decay on one side, and these are some pi mesons from the tau decay on the other side. And this is a particular class of events, 1 track against 3. You read off that that's the so-called heavy lepton, the tau. When the Z decays to quarks, you see a picture like this. So now you see many tracks with pions going, 2 bundles of tracks going in opposite directions. We call these bundles jets. That's the name we give. But basically, whenever you produce a quark or a gluon at high energy, what it does is that it rips through space. It's a strongly interacting particle, so it emits gluons. The gluons then emit more quarks and antiquarks and gluons. And eventually what you have is a whole bundle of quarks, gluons, and antiquarks going in one direction. Because of the structure of the strong interactions, it very easily emits gluons along its direction of motion, but it doesn't transfer momentum perpendicular to its direction of motion. So you get a narrow bunch of particles, again, the jet. So this is a Z decaying to a quark, which made a jet on this side, and an antiquark, which made a jet on this side. Here's an event with 3 jets. And we interpret this as a quark, an antiquark, and then that antiquark, as it was going out, it radiated a gluon that originates the 3rd jet. And indeed, if you measure the energies and angles of these gluons, they match very closely the energies and angles of photons, gamma rays, which the quarks also emit according to the regular laws of electromagnetism. So this is, again, a piece of evidence that the strong interactions are described by something like Maxwell's equations, as I told you earlier. Now, this is a very interesting event. Once again, a 2-jet event, one over here and one over here. But this actually is an event that results from a special kind of quark, not the heaviest one, but the 2nd heaviest one. And you can find that by blowing up the picture in this region. So please remember, this is a 4-story high detector, but nevertheless, it's highly instrumented. And so we understand where these tracks are to a fraction of a millimeter. In the SLD experiment, there was something very interesting done. There was a device which is about the size of a beer can, which is located just at the point where the electrons and positrons annihilate. That device was made of CCDs, pixel silicon devices. And so very close in, centimeters away from the interaction region, you would have energy ionization deposited in these silicon wafers, and you could very accurately track the tracks as they go in. Now, if you look at this vertex region, you'll see that something interesting is going on there. So let me blow it up one step further. And now you see that not all of the tracks come from this point here where the electron and positron collide. The scale here is 1 centimeter. So a couple millimeters away from the interaction point, there are 2 distinct additional vertices. And you can't help but conclude that a particle flew from here to here and then decayed. And similarly, the antiparticle flew from here to here. This is the sign of what's called the B meson. It's the meson containing the B-type quark, the next to heaviest kind of quark. The B has a lifetime of 1.5 picoseconds. But if you multiply that by the speed of light, a picosecond, 1.5 picoseconds, is a whole half a millimeter. And if you can measure very accurately, you can see something that goes half a millimeter, or actually with Einstein's time dilation, it goes a few millimeters and then decays. So this is what we call a B-tagged jet. It's a jet that contains this special heavy quark, and that's another tool that we can use to visualize what's going on in these events. So I've told you about how to find electrons. Muons, of course, are straight tracks that just go through. The heavy lepton, ordinary quarks and gluons, and these special heavy ones. And now what we can do is apply this technology on an even larger scale to understand the highest energy collisions that people have ever produced, which occur at the LHC. Okay, so now let's start talking about the LHC. This is an aerial photograph of the region of Geneva with the accelerators at CERN superposed on it. This is like Geneva. Over here is where the city of Geneva is. This is an outlying suburb called Meyrin. And you see this cluster of buildings here is the CERN laboratory. Somewhere around here is the French-Swiss border. And actually, one of the experiments that I'll talk about, CMS, is located here, which is actually in France. So the protons will go around the ring. It's a 20-mile circumference ring. And about 10,000 times a second, they cross between Switzerland and France as they go around. This is a very macroscopic apparatus. So these rings represent the various generations of accelerators at CERN. This little circle here is called the PS. That's the original CERN proton synchrotron. This one here is called the SPS. That's the 1980s era, 1970s to 1980s era proton synchrotron. This big tunnel housed the collider LEP, from which that beautiful piece of data from the Opal experiment was done. And then around the turn of the 20th to the 21st century, the LEP accelerator was ripped out, and the LHC accelerator, a proton accelerator, was put in that tunnel. Why does it have to be so large? Well, in order for a high-energy proton to stay in a circle, you have to bend it with magnetic fields. The magnets in here operate at 7 Tesla magnetic field. This is the strongest magnetic field for which you can buy kilometers of them from industry. People are working now on 16 Tesla magnets, but that's still in the development stage. Maybe if we can have those, we could have even higher energies in this accelerator. But that's not for now. That's for decades in the future. So here's a diagram of what I just showed you. Here's the laboratory CERN. Across the street from CERN is a detector called Atlas. On the other side of the ring over in France is a detector called CMS. I'll show you pictures of these in a moment. There are 2 more special purpose detectors that operate at the LHC, but they're not really relevant to the thing I'm talking about in this lecture, the search for new particles at the highest energies. They're a very interesting experimental program, so you can ask me about them after the lecture if you'd like. This is a photograph of what's inside the LHC tunnel. So these aluminum things that you see are cryostats for superconducting magnets. Of course, to make a 7 Tesla magnet, it has to be made of superconductor, because that's how you make the magnets with the highest magnetic field. In order to have 27 kilometers of superconductor, 20 miles of superconducting magnets, you also have to operate the world's largest cryogenic system. And you might remember that very soon after the original startup of the LHC in 2008, there was an accident. The accident involved a tiny hole in a piece of copper pipe, which resulted in a super leak that dumped tons of superfluid helium into the LHC tunnel. So that's the kind of risks that you take with this and the kind of accident that can happen. CERN is now completely recovered from that accident, and one of the innovations now is that the accelerator is finally, after many years, running at its design energy close to 14 TeV, that is 14,000 times the MC squared of the proton in proton-proton collisions. Here's a diagram of the ATLAS experiment. So it looks very much like the SLD experiment that I showed you earlier, except that the scale is even larger. Once again, this is the human scale. These are people in the diagram. You see the same structure, a tracking chamber, electromagnetic calorimeter, hadron calorimeter. The innovation is this thing on the outside which forms a toroidal magnetic field that winds around, oh, this is not working very well, that winds around the experiment. And the purpose of that is to image muons from their birth in the very center all the way to the outside. It's very cool. The muons in the center bend in this plane due to the magnetic field that's inside the bore of the accelerator. Then they punch their way through all that calorimetry, and then in the outside, in the toroidal magnetic field, they bend in an orthogonal plane. And this allows you to very accurately measure the energies and momenta of muons from 1 GeV, the basic scale of the proton mass, all the way up to thousands of GeV, the highest energy muons that are produced by this machine. I like to show this picture just to give you a better idea of the scale. So you see this thing here, which is a cryostat for a superconducting magnet that makes the toroidal magnetic field. This is a photograph of that thing being delivered at CERN. So this enormous piece of apparatus going in the gate at CERN becomes this tiny piece of the ATLAS experiment. Over on the other side of the ring is the competition, CMS. Maybe I should just tell you that my friends at SLAC are members of the ATLAS collaboration. This is a different design, but it's the same basic principle. Tracking, electromagnetic calorimetry, hadron calorimetry, more hadron calorimetry, and actually this iron also returns the flux of the magnet. So once again, there's a two-stage process for measuring the momenta of muons that barrel their way all through. This being over in France, 100 meters above the underground ring, is built in like tuna can type cylinders. Those cylinders, which weigh hundreds of tons, are then lowered on cranes into the LHC housing. So here are those cylinders being lowered down and assembled into the CMS detector. And so you put it together like that. There's a person. So once again, you see that in order to bend and measure these elementary particles, you just need detectors of enormous scale. Okay. And here is a typical event at the LHC. So remember, I told you that when quarks rip through space, they form jets. So when you collide protons, the most energetic thing that happens is a quark from each proton hitting each other and bouncing off at a large angle. When that happens, you get two jets of particles that go off in opposite direction. In this case, the jets have the unit GeV is the MC squared of the proton. And here you see you're well above the typical energy of a proton, or well below the typical size that you probe with a proton. So these are now hundreds of GeV. Okay, now, given that you have this apparatus, we now want to sort through the data sample of the LHC to look for unusual events. So if we're looking for heavy particles, what we want are particles that don't create two jets, but rather decay to a very large number of quarks and gluons, so multi-jet events. We might want to look for events which decay more than average to leptons, like electrons, muons, and especially taus. We might want to look for things that decay to the heavy quarks, the bottom quark or something I'll tell you about a little later, the top quark, the heaviest quark. If we're interested in dark matter, we're interested in particles that, for example, are produced in strong interactions and then decay to dark matter. So particles that are related to the dark matter particle and then will eventually decay to the dark matter particle. So if you think about what such an event would look like, it would look something like this. That you would have, for example, a particle that you create, a heavy kind of exotic quark. That particle would then decay to an ordinary quark and a particle of dark matter. You would then see a jet from the decay of that particle. It would be produced as a particle-antiparticle pair, so there would be a second jet in the event, maybe also some leptons, as you see here. And then there would be the dark matter particles, which, as I've told you already, are extremely weakly interacting. And so they go off without interacting with the detector. And then you would see an event like this, which is visibly unbalanced. You see momentum going this way, you don't see momentum going that way. And this would be the sign that somehow you've discovered this dark matter particle that must be there beyond our current knowledge of particle physics. So the simple explanation for what you would do with the LHC is you just make many, many, many of these pictures, you sort through them, and you look for characteristic events of this type. And if only it were so easy. So let me show you a couple. These are real LHC events. This one looks exactly like the one that I just showed you in that simulation, except this is actually a real event. But you haven't seen in the New York Times that dark matter has been discovered. So there must be a reason why the existence of this event is not significant evidence. There are two jets. It's visibly unbalanced. This is a large amount of missing momentum going in the opposite direction, hundreds of GeV. Unfortunately, the appearance of this event is totally consistent with the standard model. And so I have to explain to you why that can be and what we're going to do about it. Here's another event of this type. This is from Atlas. As you see, visibly unbalanced momentum. Something is missing. It's going off along the line of this dotted line. But it's not considered evidence for new physics. And so that's now the next thing that I have to explain to you. Why isn't this good enough to prove that something new is going on in nature at these very high energies? Okay, well now we have to talk about the difficulties of LHC experimentation. And these come in many levels. And so let's go through the various levels of things, problems that you have to solve in order to really do experiments at this accelerator. The first one is just data. You are drowning in data. I will explain later why so much data is necessary. But the basic reason is that the events we're looking for are extremely rare. And so in order to have any hope of finding them, you have to collect very, very many elementary particle collisions. In fact, the LHC is well equipped to do this. It collides protons with protons 40 million times a second. This has its own difficulties. A bunch of protons will collide with another bunch of protons every 25 nanoseconds. And so every 25 nanoseconds, there are electronic signals generated in this detector which make the picture. It's an event size of several megabytes. It comes off, and of course, you have to do something with it. Now, it would be nice if you could write it all into permanent storage, but a quick estimate shows you that's totally impossible. And so the first thing that happens is you need a computer system that sorts these events. And the specifications of the computer system are something like this. Your proton-proton collisions are 40 million times a second. You have a so-called level 1 trigger, which is actually a computer network that gets some signals from these events. Actually, there's not time to read out the entire megabyte of signal. You get some special signals or ganged signals. You have 100 microseconds to make a decision about whether to accept that. And you can accept 1 in 40 or 1 in 100 of those based on this limited information. Then you pass that to another level where you can pass, again, 1 in 100, and you have 10 microseconds to make a decision. Then you can pass that to something that is basically a complete event reconstruction that uses the complete information from the detector. And for that, you have the luxury of having an entire second to make the decision about whether you write this to permanent storage. Finally, you decrease this number of 40 million to about 200 events per second that you're writing into permanent storage. We say on tape, but of course it all goes into silicon these days. And let me just tell you what that number implies. 200 hertz times 1 megabyte event size times 1 year of operation, maybe a third of a year that the accelerator is on, is 20 petabytes. A peta is the next thing up after a tera. This is of the order, this is the size per year. And this size is of the order of the largest databases in the world. So maybe Google and Microsoft are an order of magnitude higher, but we don't have that kind of cache. And so these are basically the largest databases that are incorporated in scientific projects. And then you have to go through that, and you have to find one event that has the special characteristics that you're looking for. So in order to support this, the LHC actually pioneered what's called grid computing, the computer network spread out over the entire world, where you submit a job, it finds a computer in the world that has some time, it operates on it, it returns to you seamlessly the result. And so over all the nations, it's a global project that collaborate on the LHC. You have unified computer resources that are working on crunching this data to find individual special events that you would like to collect. This played a crucial role in the discovery of the Higgs boson, which I'll describe to you in just a little while. Okay, so now you collect events that look like this. For example, this is a 2-jet event with an energy of hundreds of GeV. Most of these are just thrown away because they're not interesting. That's the stuff we learned about yesterday, and we want to learn about the stuff for tomorrow. So you identify some of these which are interesting for more precise studies of the strong interactions. Many of them you just throw away, and we're looking for things that are more complicated. But for example, look at this one. This is a jet-jet mass of 4 TeV. The experiment was done at 8 TeV, so half of the energy of the 2 protons that are colliding comes into a single object which decays to 2 quarks. And actually, from the most recent data at 13 TeV, this is an event with the jet-jet mass of 7 TeV. So again, more than half of the energy that went in the 2 protons comes out in the 2-jet signal that you see here. And so this now probes distances which are even a factor of 10 smaller than that thing I showed you before, 1,000 times smaller than the atomic nucleus. And with events like this, you can begin to go in one direction toward really the fundamental interactions through which quarks interact. Here's something interesting in another dimension. This is a very complex event. Even if you look at the differences in angle, what you see is that there are many objects that appear in this event. This is actually an 8-jet event. Now you would say, that's got to be some new kind of particle. How could ordinary quark and gluon interactions produce anything that complex? But actually, here's the result of a simulation. And what you see is that 8 jets is not actually so unusual. This is the data. This is a simulation. The quality of the simulation is such that the data is actually in pretty good agreement with it. 10 to the minus 4, 1 in 10,000 quark-quark collisions in this sample would produce 8 jets. So it's rare, it's 1 in 10,000, but it's not so rare that we can consider the appearance of this event to be anything particularly unusual outside of our theory of strong interactions. Here is a 9-jet event recorded in the most recent high-energy run. So these things happen. And so just having a lot of energy is not a particular indication that you're in a new realm of physics. Well, I told you before that if you're looking for dark matter, you're interested in missing energy, unbalanced events. Events where there are tracks over here carrying momentum, but over on this side, there's no momentum being carried. And so the event is visibly unbalanced. I showed you a simulation event like that, and I showed you a couple real events as well. How do I know that those events are real? Well, there's an immediate problem that occurs to you. The easiest way to have an unbalanced event is if over here the detector is working, and over here the detector is not working. And so you have to be careful about that. And in fact, in a calorimeter, every cell is an electronic channel. And if you have millions of electronic channels, some of these might be noisy or not working, and it has to be very carefully checked. And so this is an interesting figure from the beginning of the CMS experiment. The raw signal for this unbalanced momentum looked like this. And then you go through very carefully, channel by channel. Of course, you would write a computer program to do this, to turn off the noisy channels, to mark and correct for the effects of the dead channels. And when you do that, what you see is this distribution is markedly cleaned up. And understanding your detector at this meticulous level of detail allows you to really understand that this unbalanced momentum is real in some events. Okay, now, once you've understood all that, there's a whole nother level of complexity that you have to go through. And that is that you remember when I showed you the structure of the standard model, I showed you that there are heavy particles in the standard model, in particular the W and Z bosons, which mediate radioactive decay. Those have masses of 80 and 90 times the proton mass. And also, there's a heavy quark called the top quark, which has a mass of roughly 180 times the proton mass. And these things are produced through known reactions, but they can decay to effects that mimic the effect of new particles. For example, a W can decay to a lepton, a muon, or an electron in the neutrino. The neutrino makes no signal in the detector, so that's missing momentum. The lepton is a lepton, so it's not a strongly interacting thing. It's a signal of something unusual. The Z can decay to two leptons. It can also decay to two neutrinos and just be totally missed. And top quarks can decay to multi-jets, a lepton and the neutrino. I've written the cross-sections in a unit called nanobarns. I don't expect you to know what a nanobarn is. It's some tiny unit of rate for producing these things. But the new particle rates that we're talking about are in femtobarns, nano, pico, femto. It's a factor of 1,000,000 smaller than the numbers that I've listed here. And when you go to an extra factor of 1,000,000, funny things like this can happen. For example, here's top quark production. The decay of the top quark is this. On the way out, the top quark can radiate a gluon, and actually in the production process, it can radiate another gluon. So here you can have leptons, you can have missing energy, you can have many jets which are produced. And you have to understand how all these reactions work and understand the rates of these reactions to claim that you understand the background level on top of which you're looking for a signal. Okay, well, maybe the first thing to do is to characterize all these heavy particles. And so let me now show you some pictures of these heavy particles, which actually are very cool to look at. This is a very beautiful W production event. You see the electron here, a track, and an electromagnetic deposition, nothing on the other side, so this is a W in the neutrino, just as I showed you it should appear. This is a Z event decaying to two electrons. As you see back to back, you can add up those momenta and verify that the total mass involved in those two tracks is just where the peak was in that opal diagram that I showed you. Here's a measurement of the rate. This is the standard model prediction. And as you see, the measured values are in extremely good agreement with that. Here is an event with a Z and also some jets. And so this is now the beginning of the complexity that the standard model allows us. Here we go. Now the top quark. The top quark was discovered at Fermilab in 1995. At the LHC, we're making millions of events with top quark and anti-top quark in them. The top quark decays to this bottom quark, which remember I showed you how to tag with these little millimeter vertex displacements. It decays to quarks or to leptons and neutrinos, and this leads to some already quite complex events. This is a TT bar event registered by CMS, an electron, which is, you see here, the single track and electromagnetic deposition. There are 4 jets, and there's also missing unbalanced momentum, which would correspond to the neutrino. Here's a very beautiful Atlas event with top quarks. On this side, again, an electron, something missing, and this is a B-tag jet. It's a jet for which using a vertex detector, centimeters from the interaction region, one has found one of those vertices displaced by a few millimeters from the interaction point. On the other side, 3 jets which add up to the expected mass of the top quark. And here is a very beautiful event from the new high-energy run. You see here a muon going through the entire detector, an electron registering in the electromagnetic calorimetry, and 2 jets, both of which in this case have B tags. And so you can clearly identify this as top quark production. Here is the measurement of the rate of top quark production. And without going into any detail on this slide, the green is the theoretical predicted rate in the standard model. The measured rate is in extremely good agreement with that. And both theory and experiment continue to be refined here. It's quite amazing that one can, in fact, see these numbers. And with the students, I'm going to discuss some more sophisticated aspects of this at lunch. Now, you feed these back into backgrounds. So for example, if you're interested in a muon, a neutrino, and some number of jets, 0, 1, 2, 3, 4, 5, you could try to calculate from the W production plus jets, Z production plus jets, top quarks, how many background events you would expect. And as you see, there's a great deal of complexity. The W here is the main contribution in white, but also with high numbers of jets, the top quark becomes the main contribution because the top quark already starts with some jets and it can radiate additional gluons. The sum of all of these standard model processes gives the solid histogram here. And as you see, it's in very good agreement with the data. And so this is the kind of thing that you have to understand in order to be able to look for new particles. Here's the analogous diagram with mu plus mu minus. I told you that I wasn't going to talk very much about the Higgs boson, but I did want to tell you that the Higgs boson, this question of structure in the universe, the fluctuations of this, quantized being the Higgs boson, has been discovered. The Higgs boson is the origin of mass. And so you would expect that a Higgs boson would typically decay to the most massive particles in the standard model, W, Z, and top. However, the mass of the Higgs boson is 125 GeV, which is not heavy enough to decay to these particles. So instead, it decays to anything else that it couples to. And in fact, the decay pattern is very complicated. I've listed the decays of the Higgs boson predicted in the standard model here with the percentage, the probability that each decay channel is seen. Actually, the Higgs boson was originally discovered in this mode and this mode, 2 of the rarer ones. The Higgs decays to 2 photons, 2 gamma rays, 0.2% of the time. It corresponds to 4 times 10 to the minus 13, a part per billion of the total rate for proton-proton collisions. the Higgs decays to 4 leptons through the Z intermediate state, 2 times 10 to the minus 14. So it's even an order of magnitude smaller than that. But in these channels, you can reconstruct the full momentum of the Higgs is visible, and you can reconstruct the Higgs as a bump. So if you sort through please excuse me, it's 2 trillion proton-proton collisions to find one of these events. You can then find one Higgs boson. But nevertheless, people were able to do it. Here's the photon-photon spectrum with a visible bump at this point. This is the background subtracted. This is statistically a very significant signal. In 4 leptons, here is the signal. There are only of order 20 events in this peak, but nevertheless, it's far above background. And the peak is in the same place as the bump on the previous slide. And here's a picture of one of the more exotic decay modes. This is the Higgs decaying to 2 heavy leptons. Remember, the heavy lepton can decay to an electron in the neutrino or a muon in the neutrino. So if you have 2 of them, together with some forward jet activity, which produced the W bosons that made the Higgs, you get an event that looked like this. And this is part of the evidence that the Higgs actually decays to some of these other channels, the heavy quarks and the heavy leptons. OK, so now we've characterized all these things. Now we need to apply our knowledge to search for truly unusual events beyond all of the complexity that I've described. So let's start simple. We can just look for electron pairs coming out of the LHC, and we can look and see, is there a bump on this distribution? This bump here is the Z boson, but unfortunately no other bumps. And so out to almost 2 TeV, we can see that there is no obvious signal of new particles that decay directly to electron pairs. Similarly, we can look for things that decay to, let's say, a W and a B. Here would be the expected signal for an object of 400 GeV. Obviously, it's not there. The interesting thing is this white region. The white region, which extends out to 800 GeV, is the signal that you would expect from a top quark plus extra gluons that are produced in association with it. And so you have to understand in detail the normalization of this white curve to claim an excess over it. And people have been able to do that by very accurate and meticulous calculation. To search for missing particles, these searches get more sophisticated. Typically, one takes some well-chosen variables. I'm going to tell you what MT is in a minute. You look for regions that are well separated from your signal. You measure the distributions there in order to normalize your model of the background. And then the model of the background has to be extrapolated into this region. And then you see whether there is an excess above background. Here are some examples of plots like that. You see that these background calculations are very complex. This one, which is a search in jets plus missing momentum, the main contribution is from a Z, where the Z decays to neutrinos that are not observed. That's the solid black. But you see there are also contributions from W, top, in green, et cetera. Only when you add them up do you see that you actually account for anything, and there's nothing left over that would be a new particle. Here's another such distribution. Here the main contribution is from, again, the Z, W, top is red. One sorts through many, many of these distributions to see whether in the tail, perhaps, some new effects might show up. Occasionally, there are you have to invent new variables to try to separate the signal from background. I think there's not time to talk about this, but you can ask me about it. In any case, that variable, transverse mass, has the property that for something where you have a W and a neutrino, that quantity is bounded at the W mass 80 GeV. And you see how the background falls off precipitously when you go above 80 GeV. But unfortunately, on the other side, there's still no excess. Okay. Well, some anomalies do appear at this early stage of the run. We don't know whether they are real anomalies or whether they're just statistical fluctuations. Here's an anomaly in the search for top quarks plus missing energy. So this would be a model, maybe some of you have heard of something called supersymmetry. So this is a search for supersymmetry. You see there are a couple extra events in the signal region here, which lead to the fact that you can't put good limits, but maybe this is a real signal. We'll find out as we accumulate data. Right now, it's just a couple events of fluctuation. This is the gamma-gamma curve, the analogous of the electron-electron curve that I showed you before, reported by Atlas in December of 2015. And you see this little bump here. So this is actually marginally statistically significant. It's made a lot of noise in the press, the quote, 750 GeV resonance. And it certainly got the theory community excited. There are now 400 theoretical papers about what this could be. And whether it's real or not, well, they're accumulating data now. We'll find out in a couple weeks whether it becomes larger or whether it just goes away, whether it was just a statistical fluke. And here's one more. This is a WW resonance at 2 TeV, which was found in the earlier LHC running. And they're now trying to accumulate enough data to see whether this is there at the higher energy. So maybe new physics is peeking through. Maybe we just have to wait a lot longer. So now the last thing I'd like to say is, what's the long-term course? And let me just say, we've just now come from an energy of 8 TeV in the previous run to 13 TeV today. The LHC is rapidly accumulating data, and we're just beginning the search for new particles at the true design energy of the LHC. So here is the accumulated luminosity for each year, 2011, 2012, then there was a long shutdown now, 2015 and 2016. Here's where we are today, or maybe a week ago. We're accumulating data at the highest rate yet in the history of the LHC program. And this purple line is all at the highest energy. So we'll see where we get to by the end of the year, maybe 25 or 30 of these funny units, inverse femtobarns. I'm going to quote numbers now in inverse femtobarns, and you'll see how they are supposed to accumulate over the years. This is the roadmap for LHC published by CERN. And as you see, once we've got this enormous machine, we now have to exploit it. And it's going to be exploited over decades, as you see. So right now, we're here. There'll be a phase 1. There'll be an upgrade. There'll be some more running here. There's a major installation of new equipment. The luminosity, the event rate in proton-proton collisions will be increased by a factor of 10, and then it's expected to run for another decade. So where we are now is 10 of these inverse femtobarns. In 2018, 100. In 2023, 300. By the end of that decade, 1,000, and it's supposed to run out to 3,000 of these units. So far, we have only seen a few tenths of % of the entire data sample of the LHC. What will be there? We don't know. I've told you problems that we would like new interactions to solve. I've told you the methods by which we will search through this data to find those new particles. I can't tell you they're there. You just have to wait. I'm sorry. But I think you see that there is a golden opportunity here to really break through to the next level of interactions in physics. And hopefully I can come back to this audience and report some results sometime in the future. Well, thank you very much.
Thank you for a fascinating talk. So we can take questions.
Okay, please feel free to leave if you're late. I'm sorry I've gone over time, but I'm happy to take questions.
Great. Well, start off.
You mentioned dark matter and the weakly interactions, maybe, of dark matter. Is there experimental evidence that any weakly dark matter interacts at all in these, other than gravity?
No, there is no, well, this is a disputed statement. There are people who write papers that dark matter must interact because, for example, the cores of galaxies are more smooth than would be expected if dark matter had no interaction except for gravity. Personally, I'm not a believer in that. I would say there is no evidence that convinces me that dark matter has any interaction other than gravity. However, I'm a theorist. So when I make a model for dark matter, those models must fit together with the rest of what we know about physics. And so the kind of model for dark matter that I like very much is a model that not only explains dark matter, but it also explains these other problems that I've talked about. And in those models, dark matter is part of a new sector of particles, some of which have large production cross-sections at the LHC, and all of which have some weak interaction. But, okay, you could just say, well, that's your theory, and someone else can have a theory where dark matter is extremely weakly interacting and can never be produced in these experiments. And we don't know. It's, both of those are open questions right now.
So here's another theory question, but it's based on your standard model slide, so I figure it's fair game. You had the Higgs boson in the middle and all the particles outside and then the particles beyond that. And some things bothered me about that slide, in addition to the lack of, you got the weak and strong and electromagnetic, but you don't have gravity, you don't have dark matter, and from what you just said, those two omissions may be related.
Yes.
But a third question that bugs me from a cosmological standpoint is, why is there more than one kind of particle? And is there a reason for having more than one kind of particle in the cosmos? And because it seems like if you've got 20 of them, why not 1 million? Why not 3? Why not, that seems very arbitrary.
All I can say is I couldn't agree with you more. And I mentioned at several points earlier in the talk that the reason for the multiplicity of particles is actually one of the deep mysteries of particle physics. The standard model has nothing to say about it. It doesn't mind if there are 3, 6 quarks, 8 quarks, 4 quarks. It doesn't much care. There are some things that we know about this. For example, there's a phenomenon in particle physics called CP violation, or maybe it's better thought of as T violation. The fact that the equations of motion do not give the same answers when you run them forwards and backwards in time. So within the standard model, you cannot have T violation. So first of all, CP and T violation are observed properties of particle physics. In particular, at SLAC and at our sister laboratory in Japan, KEK, over the past decade, there were very beautiful experiments that looked at the decays of this B meson, this heavy quark meson, of which I showed you some examples in this slide. And you can actually compare reactions where you have BB bar, and B goes to A, and B bar goes to B, and you can compare the case where B to A happens first and B bar to B happens later, to the case where B to B bar happens first and B to A happens later. And by looking at that data, you can see that there's visibly 100% scale T violation in that process. So this really exists. Okay, now, can I accommodate it in the standard model? Well, it's very delicate. In the standard model, if you only have 4 quarks, you can't accommodate it. But if you have 6 quarks, there's a parameter that you can adjust to turn this on. Okay, so maybe that's a reason why there are 6 quarks. Now, in order to generate the baryon-antibaryon asymmetry in the early universe, you also need this CP and T violation. And it is actually generated with this parameter. But unfortunately, in the standard model, you don't get enough. To generate the number of baryons that we see that we're made of, you need that the initial radiation in the Big Bang had about a part per billion extra quarks than antiquarks. But in the standard model, you can only get a part per billion billion. You miss by 9 orders of magnitude. So that probably means that there's some other kind of new interaction which also has CP violation and which is able to produce this asymmetry. But if you have that, why do you need 6 quarks? Okay, well, then it goes around in circles. We don't know the answer to this question, okay?
Thanks for a wonderful talk, Michael. It was really great. It strikes me the main advance in the experimental side is bigger pieces of metal, more electricity, bigger magnets, more cryogenics, and so on.
And more data, and the ability to deal with it. That's very important.
I'd like to invite you to predict the future of technology, which may be unfair, but is there any hope that there'll be some new technological advances that will make it simpler to generate the data, so to speak, and that 100 years from now people will laugh at the size of the pieces of metal that people put together? Or is that fundamental physics makes it happen that way?
Well, I think we can see advances in a couple dimensions. First of all, for the accelerator. There are advances in the technology of accelerators that we're seeing now that will make accelerators much smaller. And so right now we're doing experiments at SLAC with electron acceleration, where you get basically 1,000 times more punch for a given length than you do in these experiments or in the electron experiments of today. And so we're trying to develop new technologies for acceleration that will make these things maybe 1 kilometer instead of 20 kilometers. Although by then we'll probably want one 20 times as large, but at least it won't have to be 20 times larger than this. The other thing is, of course, microelectronics. So as you can make silicon or germanium devices with much smaller pixel size, you can record tracks more accurately, and then you have some advantage. Also, the speed. So typically in these experiments, you look at nanosecond timing or even microsecond timing in most devices. And now people are talking about new technologies with picosecond timing. But on the other hand, if you have a very relativistic particle, it's just very hard to do anything with it. If you have a Tesla field and you have 10 meters, it only bends by millimeters. And so you need meters of stuff to measure the angle of deflection. If you have a high energy pion, which is hundreds of GeV, and you put it through a block of iron, that iron has to be 5 meters thick to range it out. And we don't know what to do about that. So the detectors of the future will be, if anything, larger than the ones now. But of course, the instrumentation will be much more powerful and sophisticated. And the rates will be smaller, because if you take beams of a certain size and you try and shoot them at each other, and you want to see the smallest distances, it's just going to be harder to get them to hit with that close a separation. So the rates are going to go down, and our data collection rates have to go up by orders of magnitude. But I think the technology will be able to deal with that. As our computers get smarter, we'll be able to find a small set of very interesting events in larger and larger data samples. And I think I've told you the LHC already solved some extremely challenging problems already to get to the level we are. So once again, the Higgs boson required 2 trillion proton collisions per event to discover the Higgs boson, and people succeeded in doing that. So that's already a kind of milestone.
All right, I'm very sorry, but we have to close up and finish the questions. So it was once again.
Some
let's thank
people
our
looked eager.
speaker
Can we
for
take one
very-
more? Okay, very good. Anyway, come up here afterward. I'll answer your questions privately. Thank you very much.
And very quickly, I want to offer you a highly prized coffee mug
Oh,
from SETI Talks,
okay.
and thank you for the presentation.
Oh, I see. And the video can be found at SETI.org Talks.
Yes.